Alrighty. So, oops. The assignment 1, that's due today by 5, and I'll have the solutions up sometime after that, shortly thereafter. Any final questions before we move on? Anybody? Okay, all right. So the second assignment is up, and that'll be due on the 10th. So right here. Now, if you do me a favor, on number 2 here, so you're going to fill in each square or rectangle, I guess. I said square. Fill in each rectangle of this chart with true or false. Like, here's the predicate logic statement, here's the domain, and then it's true over that domain or false over that domain, and you tell me which is which. So when you answer this, make sure your answer is is in the form of a chart here, like this. I mean, if you printed out this chart and actually filled it in, that would be great as well. All right. So that's due on the 10th. So we'll talk about that as time goes on here. So, any other questions about anything? Anything so far? So let's do some more examples of predicate logic statements over different domains, and see if they're true or false. So more examples. So let's take a few statements. So a couple with just one variable, and a couple of them with 2 variables. So for all x, let me see, make sure I don't do for all x yeah. So we'll say EX means X is even, and FX to mean X is a multiple of 4. So X is even mean X is a multiple of 2. FX, X is a multiple of 4. And OX will be x is odd, and px will mean x is prime. So consider the following. For every x, ex or ox. And let's look at some domains. So we'll say the entire set of integers. So that's 0 plus or minus 1 plus or minus 2 plus or minus 3, so on and so forth. And let's look at the set of negative integers that are even. Minus 6, minus 2, or it's minus 6, minus 4, minus 2, 0, and then positive integers that are odd. And then maybe we'll look at just the positive integers. All right. How about the statement, for every x, x is even or x is odd? For every x, x is even or x is odd. What about this domain? True or false?
True.
That's true, certainly. What about the others?
They're all true.
They're all true.
Yeah.
Now, here's something slightly different. It may seem the same at first, but it's not. So let's keep in mind what's known as the scope of a quantifier. So the quantifier is for all x or there exists x. So a quantifier applies only to the predicates immediately to its right. Immediately to its right. So, for example, if I was to write for all x, so let me not use these, Rx implies Sx, the scope of this quantifier applies to the statement immediately to its right. Okay, so this quantifier has this scope. This is the statement immediately to its right. If I was to write something like this, for every x, Rx implies Sx, now this quantifier here, the scope is only this. And this is unquantified. So if you want this quantifier to apply to all that, you have to put it in parentheses to say the scope of this quantifier is this parenthetical expression. If you did something like this, okay, the scope of this quantifier is only right here. So what you can do, also is something like this. Oops. For all x we'll do it in existential. There exists x, Rx implies there exists x, Sx. So now the scope of this quantifier is right here. And the scope of this quantifier is right here. And the x's are different. I mean, you could write like a different variable there entirely if you wanted to. You could use a y instead. Let's set this up poorly. Let's see.
So that expression is different than the parenthetical expression, or could you?
Oh, hold on. I just wanna. I should introduce this and then put more examples down below. Okay, I'll fix that later. Okay, go ahead. So I'm sorry. What do you want to say?
So could you, I guess, simplify that expression, and then would that be the same as having,
No, absolutely not. It is not the same as having there exists Rx implies Sx. Yeah,
Okay.
they're very different, right? And so these x's are different, and then this is the same as the same meaning, i.e., logically equivalent, as this. So if you were to write there exists x, Rx implies there exists y, Sy. You could write that if you want, use a different name for the variable. But this quantifier, this x is quantifying, this there exists x is quantifying that x. Here, this there exists y is quantifying this y right here. It means the same thing. So sometimes people just keep the same variable just to simplify the expression so you don't have a bunch of letters running around where you don't have to. The point is this quantifier scope is here, this quantifier scope is here, so they're two different things. And then this is different than. There exists x, Rx implies Sx. Totally different than that. So, for example, down here, okay. If I was to write for every x, ex, or for every x, ox. Now, read what this says. This says for every x in the domain, x is even or x is odd. This says for every x in the domain, x is even, or for every x in the domain, x is odd. Well, truth value of that for every x in the domain, x is even. Or, for every x in the domain, x is odd. Is everything even or everything odd here?
No.
No. False. Here?
It's also false.
Also false. Here again false. The only type of domain over which that would be true would be a domain that only consists of even numbers. Let me see if I can make one space for it. Or only even or only odd numbers. So if we were to have a final thing like this, say just the odd positive integers 1, 3, 5, 7, 9, 11, 13, so on and so forth like that. Here, this is true, right? Because everything itself is odd. All right, so they're very different types of statements. Okay. For every x less than 0 implies x is even. For every x less than 0 implies x is even.
They're all false except for the second column.
All false. Well, what about this one? For every x is less than 0 implies x is even. Well, you have -3 in there, for example, so it's false. All right, so not every x in the domain satisfies that. What about this one? For every x less than 0 implies x is even.
True.
True, yeah. Pick an x less than 0. If you have x less than 0, well, it's even. So this is true and that's true. Pick an x bigger than or equal to 0. These guys here. What happens to the implication here? For any of those numbers there.
X is greater than 0.
Yeah, so this is right here. The hypothesis is the hypothesis is false, which makes the implication true. So for every x, either the hypothesis is false, or the hypothesis is true and the conclusion is true. All right, so this is how you sort of quantify over a subset of the domain. So here, this domain is just some set of numbers, and I'm trying to quantify just the negative stuff within that domain. Forget about the positive stuff. So if I want to say something about the negative stuff in the domain, that's what I write. For every x, when x is negative, you get that x is even. That's what I'm trying to say. So I'm excluding the positive stuff in 0 from consideration. Right? Or I could put less than or equal to 0 or whatever. Okay. For every x less than 0 implies x is even. For both of these, the answer is the same. It is
True.
true. Why is it true for both? For every x, what?
The hypothesis is false.
And for every x, the hypothesis is false. So for every x, the implication is true. You know, it's vacuous. It's vacuous, but it's still true. Okay, you have to have the vacuous condition somehow defined, so there it is. Again, why is implication in the vacuous case? Why is it considered to be true? Basically, so you have the implication tautology, so that P implies Q is logically equivalent to P naught or Q, right? Because P implies P naught or Q, this disjunction. If you don't have P, right, then you must have Q. So that's P naught or Q. Or, well, if you put the naught over here. If you don't have P, then you must have Q. In other words, P naught implies Q. So, as a matter of making things equivalent to disjunction, implication equivalent to disjunction, you need that vacuous case to be defined as true. Because it matches the rhetoric in English. If you don't have P, then you must have Q, which is the same as P or Q. All right, how about this? For every x is prime implies x is odd. For every x is prime, right? P of x is prime. O of x is odd. Well, what's a prime number? What's a prime number? Definition.
Can't be divided by anything.
Can't be divided by anything except
Itself.
and 1, right?
1.
So the only divisors, so an x is prime when the only divisors, an integer x is prime when the only divisors of x are 1 and x. Okay, so, well, are they all odd, the primes? All primes are odd. Well, if you had an even number, one of its factors is 2. So it won't be prime. Unless you're talking about what?
0.
Well, yeah, 0 isn't prime. Everything divides 0. Right. Dividing 0 into n parts is 0, right, all the time. So everything divides 0.
1 and 2.
Well, 1 is actually not considered to be prime. I mean, you could consider it to be prime, just as a special case, it's not. 2 itself is prime. The only divisors of 2 are 1 and 2. You may think, oh, it's kind of cheesy to say that, because there's just nothing in between 1 and 2, so it has to be true. That it's prime, that it satisfies that definition. I mean, there's better reasons for it other than that. I mean, that's a reasonable objection. But why it's included within the realm of primes, there's a very special reason for it that we'll actually cover later on in the semester. But 2 itself is prime. Okay, so 2 is here, as is negative 2. So here it's false. So prime implies odd, right? Like x equal to 2 is prime. So remember, 2 is prime. It's the only even prime. The only one. This one, well, there's 2 again, so it's false. This one, there's 2 again, it's false. How about this? If x is prime, then x is odd within this domain.
True.
It's true. Everything's odd. They're all odd. Whatever implies odd in this case. So again, these are all examples of, again, in propositional and predicate logic, we're being totally literal about things. There's no implied meanings, no nothing. Okay, it's all, there's no innuendos or anything like that. These are all false for all x because x equal to 2 is prime and it's even. That's the only example. Other than that, it's always true for every other x in the domain, but that doesn't matter. Okay, if you wanted to write this, for every x not equal to 2 and x is prime, implies OX. Well, terrible looking. Try that again. For every x is not equal to 2 and x is prime, implies x is odd. Well, what about here? Since x equal to 2 is the only exception to the odd prime rule, here it's going to be what? If x is equal to 2 and x is prime, well, when is an implication false? When is an implication false?
When the hypothesis is true and the conclusion is false.
Right. So to make the hypothesis true, right? To make the hypothesis true inside here, I have to have x that's prime and not 2. So 3, 5, 7, 11, 13, 17, 19, 23, 29, so on and so forth. 89. 89 is my favorite prime. Aside from 2. I don't know. It's either 2 or 89. All right. So this is true. These are all true. And this one as well. However, again, we're still kind of being cheesy in this instance because why? Right? I mean, if I was to say to you, for every student in this class everyone in this class is a student of mathematics, including me. Everyone in this class is a student of mathematics. I mean, is that true?
Yeah.
Yeah, I mean, but, it's a math class, so you're kind of being, sort of weird about it because you're already dealing with math students, right? So, I mean, there's a whole, world of math students, at Wright State, and, to say that, you in this class are students of math is kind of not telling the whole story. So for this domain over here, I mean, what's actually true is that everything is odd. So this statement, false, 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 true. All right. Let's see. Let's do some 2 quantifier statements. So, I guess I'm going to have to move these over. For every x, there exists a y such that x plus y is equal to 0. So we've looked at this one a few times. For every x, there exists a y such that x plus y is equal to 0. Well, that's true here. What about here? For every x, there exists a y such that x plus y is equal to 0. So you pick an x, there is a y that depends on x, for which I can add x to y and get 0.
False.
False, right? Which ones, for example, don't don't have their partner.
1,
That's
3, and
here.
5.
Yeah, 1, 3, and 5, right? So it's false here. Here and here. Well, nobody has its negative present, so it's false here. How about this? For every x less than 0 implies there exists a y such that x plus y equals 0. So for every x less than 0 implies there exists a y such that x plus y is equal to 0. What about here? So, I mean, the only time an implication is false, again, is when the hypothesis is true and the conclusion is false. So forget about the hypothesis being false. It's irrelevant. The hypothesis being false is irrelevant. So just think of when the hypothesis is true, right? We need that the conclusion has to be true as well. So for all the negative numbers in here, does there exist a y such that x plus y is 0? For every negative number in here. True? False?
True.
True. How about here? For every negative number. Well, you were saying it earlier, right? The ones that didn't have their negatives along with them were the positive odds. But for the negative numbers, what? The negative
It would be
numbers,
true.
it's true. What about here and here? For every x is less than 0 is false. So again, these are both
True.
true. Again, vacuous. You don't have to state that it's true vacuously. I mean, it's just something I want you to be aware of. Okay? So, lots of examples there. So, on the homework, assignment number 2, here's, question like that. A chart, 3 different domains, a bunch of predicate logic statements, and then you fill all those rectangles in. I'll update that to say rectangles. I don't know how that slipped past the goalie, that one. Alrighty. So that's the basic of predicates. Let's talk about translations. So translating English language statements into predicate logic statements. So some languages in English you can use just propositional logic with. These are statements that don't use quantifiers. When you say some or all or there exists or something like that, then you're getting into the notion of predicate logic. And even predicate logic doesn't capture everything that we talk about in English, although it captures a lot of stuff. What we're doing is called first order predicate logic. There's also second order, third order, fourth order predicate logic, which is similar, not that much different. But then there's even stuff like fancier stuff called modal logic, which we're not going to get into. So consider a large domain. Something like, so large in quotes, of course, something like the universe and everything in it. Okay, what we want to do, so we want to write predicate logic statements with the same truth value as English language statements when appropriate. So when propositional logic is insufficient. So we want to write predicate logic statements with the same truth value as English language statements when propositional logic is insufficient. So two main principles for doing this are as follows. One, so whenever, and we touched on this earlier, quantifying, over domain D. So the domain D is always going to be like something, something bigger than, the specific things you're talking about. So since that's the case, so you think of D as being the whole universe. So D is the whole universe, or D is the set of real numbers when you're just, talking about properties of numbers or something like that. But when you're talking about properties of numbers, typically you're gonna talk about some subset of those numbers, like the integers, right, or the positive integers, or something like that. Or if you're talking about the whole universe, you're going to be talking about some subset of that. Well, all people in the universe like chocolate, something like that. So, you're actually talking about people. You're not talking about, like, asteroids and things like that. So what you need to do is, whenever quantifying universally over some subset of your domain, of your large domain D, write for every x, P of x implies, whatever property you're talking about. Oops. Y-O-U apostrophe. Whatever property you're talking about. And then in this here, where P of x identifies the subset you're talking about. So for example, if you want to say, so h of x is a horse, and b of x is brown. If you want to say, and D is the whole universe, and you want to say all horses are brown. All horses are brown. Right? What you would write is, for every x, so the domain is the whole universe, but I'm only talking about what? I'm only talking about horses. Right? So only horses I'm talking about. So all horses are brown. So what I want to write is, for every x is a horse, implies, x is a horse, implies something. All horses eat grass. all horses, have a favorite brand of horseshoe. All horses, pack a lunch and go to school in the morning. I mean, whatever it might be. Here, we're just saying all horses are brown. So if it's a horse, then it's brown. You don't write for all X, be X. Not this. This means everything is brown. Everything in the universe is brown. For all X, be X. For every X in the universe, X is brown. Here I'm saying all horses are brown. Okay, so let's analyze that statement. Does it have the same truth value as this? In other words, I'm not saying this is true. I'm not saying it's false. Okay, all I'm saying is whatever the truth value of this might be, okay, this has the same truth value. So consider the universe that we live in. Is it true that all horses are brown? Certainly not. Right? I mean, we've all seen what? The proverbial what? We've all seen the proverbial what? Are all horses brown? No. How do you display the fact that it's false that all horses are brown? You have to show a
There exists.
yeah, but there's a proverbial thing. Kind of 18th century talk. Sorry, 19th century talk, I guess. You have to show me a horse of
Another color.
yeah, horse of a different color, right? You ever heard that saying? Yeah, that's a horse of a different color. So you have to show me a horse of a different color. In other words, there does exist a horse X. So Harold the horse, X is a horse, so that's true. I mean, so Harold the horse, he's a horse, that's true. But Harold the horse, he's black, right? So that's false. Well, or he's white. So that's false. Right? So this is true, that's false. Makes the statement false for at least one horse, right? So for Harold the horse, or for Black Beauty, or for, whoever else, some other horse that's just not brown. He's white, or he's black, or he's, what are other colors that come in? Pretty much white, black, and brown, right? Different shades of brown. All right, now suppose we live in an alternative universe. We live in an alternative universe where, yes, indeed, all horses are brown. There's no such thing as a horse that isn't brown in the universe that we live in. This alternate universe that we're going to be occupying suddenly. Okay, so in this alternate universe that we're occupying suddenly, okay, this is true. All horses are brown. So if it's a horse, then it's brown. So this would be true as well. Just think of when the hypothesis is true. In this alternative universe, all horses are brown. So if I picked an X in this universe that made that true, well, because it's this alternative universe of brown horses, that's true as well. So whenever the hypothesis is true, the conclusion is true. If the hypothesis was false, I mean, if we picked in our alternative universe, we picked X equal to a table, right? This table here. Well, this table is not a horse. So that would be false, but then that makes the implication true. So you don't worry about the hypothesis being false. When the hypothesis is false, it's always true. The implication is always true. So all horses are brown. What about something like this? No horses are brown. I'll do a separate example. No horses are brown. So, as I was saying before, when you say no horses, or no numbers, or no students, no homes, no something, that's universal quantification. But it's universal quantification of a negative statement. Right, so no horses are brown. Say it without the no in the subject. So here, right, this is the subject, that's the verb, and that's the direct object or the predicate. Right? Say the negative over here rather than in the subject. Right? It's the same as saying what? All horses are. No horses are brown is the same as saying all horses are, and then the negative moves over here, are what?
Not brown.
Not brown. Right, so in predicate logic, so all horses, again, for every X, right, X is a horse, implies what? All horses are not brown. For every X, X is a horse, implies well, it's the same as this one. All horses are brown. HX implies BX for every X. All horses are not brown. For all X, HX implies implies what? Instead of BX, it's just B. Right? All horses are not brown. B not X. You can put the negation here like that if you want. I know it's the same notation as derivative, but we're not doing calculus here. Shouldn't cause any confusion. How about this? Only horses are brown. Only horses are brown. This is also a universally quantified statement. Can you say it as all something or something? So only horses are brown. So just horses. Not trees, not the dirt, not not your brown shoes. Those aren't actually brown. Nothing, just horses. Not bears, just horses. Only horses are brown. Can you say it as an if-then statement? Can you say
Yes.
it as, sorry, go ahead.
You could say it as if it is brown, then it is a horse.
Yep. Same as if it's brown, then it's a horse. Exactly right. Right, so this is for every X, what? If it's brown, then it's a horse. Right? BX implies HX. Right, or you could also say for every X, if it's not a horse, then it ain't brown. Either way, if it's not a horse, then it's not brown. Right, that's the contrapositive. The contrapositive is that, P implies Q is the same as Q naught implies P naught. All right, so those are all examples of universally quantified statements over the whole universe. Right, so all horses are brown is for all X, HX implies BX. Not this. For all X, BX. That means everything in the universe is brown. That's not what we're saying, right? We're just saying something about horses. But typically, when you're talking about, something, right, the domain in which you're making your discussion is something big, right? Typically like the whole universe, right? So, if you're just talking about life, you're typically talking about the whole universe or things, within the natural world. If you're talking about mathematics, maybe you're just talking about numbers, in which case your domain might be all real numbers. Or, whatever other mathematical objects you're talking about besides numbers. So all horses are brown. No horses are brown. Remember, when you say no horses, or no horses are brown, no dogs are green, no potatoes are purple, whatever it might be, it's the same as saying no horses are brown is the same as saying all horses are not brown. It's universal quantification, not existential. And then this only construction, it kind of flips the implication around. Only horses are brown. It's the same as saying if it's brown, then it's a horse. Or if it's not a horse, then it ain't brown. All right, so that's principle number 1 for universal quantification. For existential quantification, quantifying over a subset of your domain identified by P of x, right? So with universal quantification, it looks like this. For every x, P of x implies whatever property you're talking about. If you want to do, existential, you do this. There exists x, P of x, and whatever property you're talking about. So for existentially quantifying a subset, you always use conjunction. For universally quantifying a subset, you always use implication, and never the other way around. All right, so for example, we'll say P of x means x is a potato. And, we'll do brown again. B of x is brown. All right, so if I want to say, well, some potatoes are brown. Is there an E? Yeah, I think there's an E. Some potatoes are brown. Do you guys know the whole controversy or whether there's an E at the end of potato? Probably not. You're probably too young to remember that one. Anyway, some potatoes are brown. Well, what are we saying? We're quantifying over the whole universe something about potatoes. So some potatoes are brown. Some potatoes taste nice. Some potatoes you can bake them. Some potatoes you can fry them. Right? So some potatoes are brown. There exists an X in the universe such that X is a potato and X is brown. Is this true? Certainly it's true within the whole universe. Certainly this is true, over the whole universe. I can go to the grocery store right now and find a brown potato. Is this true? Well, there does exist an X in the universe down at the grocery store. That X is a potato. It is true. And, that X is brown. So this is true and that's true. It's conjunction. That makes it true. So some potatoes are brown. Not all potatoes are brown. Not all potatoes are brown. Not all. Right? I mean, if I was to say not all horses are brown, that's true because there exists a horse of a different color. Not all is the same as exists. Negating all is there exists. So not all potatoes are brown means there is a potato that isn't brown. Right? A yellow potato or a white potato or whatever. You could maybe say it's still brown, but whatever the case might be, there exists X, there is a potato that isn't brown. There exists X and it's not brown. So not all is the same as there is. Similarly, if you want to say there isn't, right? So there is there exists. There is not is actually for all. Negating an existential, I'm sorry, time's up. We'll talk more about that next time, all right?